Hi everyone, it's Mr. Youngren again, and we're going to continue our work with exponentials and logs, but still just working with exponentials today. Last time we went ahead and just reviewed what exponential growth and decay, kind of extending on that the growth and decay and talking about how we can compound that growth and decay in different ways. But today we're going to graph exponentials, which is something that you did quite a bit of in Algebra 1, which was a while ago. But we actually did this back in first semester when we were graphing all our mother functions. So going to be kind of somewhat of a review. It's probably been a while, so definitely a refresher is needed. So let's go ahead and jump into it. We're going to pick up on page 172. So on page 172, all this first page is an opener. And I don't even want you to write the equation here. Rather, I'm just going to have you identify if you see HA, that represents the horizontal asymptote, and then the y-intercept. So why don't you go ahead and just take a second, write all those things down, as on the next page, we're going to actually try to make some connections between what we see in the equation and what we see on the graph. So go ahead and identify horizontal asymptote, y-intercept, and then even, why don't you start thinking about these questions, 1, 2, 3, and 4, on the following page. Hit pause to do this, and then you can unpause once you're ready to keep going. All right, welcome back. Hopefully you were able to identify the horizontal asymptote and y-intercept, as there really wasn't too much to that. And on top of that, hopefully you got a chance to start thinking about these questions, because this is really what we want to focus on. So I have these pages right next to each other so I can kind of refer back to them. But let's talk about these questions, because that's the important piece here. So the first question is asking, do we see the horizontal asymptote in the equation? The answer should be yes. That horizontal asymptote shows up after the exponential term. So what I mean by that is that it's the exponential term here is 2 to the power of x. So that plus 4, that's where my horizontal asymptote is. And you'll notice on all my graphs here, I'm actually filling in where that horizontal asymptote is with a line. It's really helpful, especially as it's real common for students kind of go in between, whether they think it's -3 or -2 or even -4. But I know that it's really the horizontal asymptote wherever the graph starts to get really flat at. And so I always draw that in so I can physically see where it's at. Now, when I'm writing the equation, it's these equations of horizontal lines are y equals whatever that number is. So to sum that up, the horizontal asymptote shows up after the exponential term. And this is also a vertical shift. When you think back to what we did first semester, we talked about transformations of all of our mother functions. And the term that came after our kind of like that function term, in this case, the exponential term, that's our vertical shift. So whatever number we see there, that's that horizontal asymptote. You might hear us refer to it as the bottom floor every now and again. Then the next question, this one was kind of tricky, and it's asking the relationship between the distance of the y-intercept, so from here back down to the horizontal asymptote, in that part in the equation. So if I look at the distance here, I'm having to go up 1, 2, 3, 4, 5, 6, 7. Over on this one, I'm having to go up from the bottom floor, 1, 2, 3, 4, 5. Now, do I see a 5 and 7 in those equations? Absolutely, right? That 5 is that number in front of the exponential term. That 7 is the term in front of the exponential term as well. So however far up we're starting from that horizontal asymptote, or however far up the y-intercept is in this case, is our a value. And so the a value is kind of like our stretch or shrink factor or stretch or compression. And so what I wrote down here is that the y-intercept is a, if you think back to our mother functions, a is the first number after the equal sign, above the horizontal asymptote. Now, once we throw in a horizontal shift and these graphs start moving from left to right, this rule changes slightly, and we'll have to kind of adjust for that. But again, that's just a nice thing to think about. So anytime we see our horizontal asymptote, if we don't have a horizontal shift, that our y-intercept is a above that horizontal asymptote. All right, last couple questions, kind of just a basic understanding of exponentials, but what determines whether a function is increasing or decreasing? I'm thinking more of the equation here, and we know exponential equation is increasing if the base is greater than 1. So in all these cases, 2 is much, or not much, but it's greater than 1. 3 is more greater than 1. And so that's why we see the graph increasing as we move to the right. And that's what it means for a function to increase, is as x gets bigger, is y also getting bigger as well. Now, the opposite of that a function is decreasing if the base is between 0 and 1. That's really important because it's really easy just to go the opposite and say, yeah, if it's less than 1, but we actually won't see negative bases. So really, if we ever see a base between 0 and 1, so meaning it's going to be some sort of decimal or fraction, that's when we know that function is decreasing. And you kind of saw that back in the last lesson when we talked about exponential growth and decay. All right, now the last thing is, what if we forget all these relationships? What if we have no idea or don't remember how I graphed exponential equations in Algebra 1 or how we did it with mother functions? Well, you can always do what we might call tee it up, which means just to make a table of values. And so you just put together some x's that you want to plug into your equation, plug them in and see what you get for y, and just plot points and connect them. You can do that for any function. So there really is no reason why we should not be able to graph any equation, whether it's new to us or something we've seen before. All right, well, let's jump into it and let's actually start graphing. And with a lot of the things you've seen in this notebook is that we will always provide some explanations as to how we're going to go about doing this. So here's kind of the general form of exponential equations. And here's some notes for it. So if b is greater than 1, the graph will be increasing. We talked about that above. If it's between 0 and 1, it'll be decreasing. K, or that number after the exponential term, is our vertical shift, giving us our horizontal asymptote. H is our horizontal shift. This is what I talked about when I was referring to how far above the y-intercept is from the horizontal asymptote. We did not see any horizontal shifts in those opening problems. So we might have to slightly adjust for that when we see those, and we're going to actually see them right away. And then A is the initial value, so kind of how far up we're going to go from the bottom floor, and we can use that relationship from the opener to find your first point. All right, so let's put this together. Now, number 5 does not have a horizontal shift, and I know that because there's not a number added on to the x. Horizontal shifts always show up when they're being added or subtracted onto our x in the equation. So let's start with this. And one thing that we like to do, if we think back to our mother function unit, is kind of recreate our axes. So we have the general x and y axes on our standard coordinate grid, but we like to recreate them based on those shifts because then we can kind of replicate graphs. And we're going to actually do that a little bit right now. So the first thing I always start off with when I'm graphing is that horizontal asymptote, which is at -7. And I fill that in with a dashed line. The next thing we want to figure out is, where do we want to put that first point at? And it depends on that A value. And that's what we were trying to get you to think about in that opener there. So if I look at this equation, the A value is 3, which tells me my first point on the y-axis, which has not shifted, right? If we're thinking about our horizontal shift, is 3 above this floor right here. So up 1, 2, and 3. Now, how we continue to get more points is we start using the multiplier. So right now, this point is 1, 2, 3 above the bottom floor. Our multiplier is 2. And so we're wanting to take this distance of 3 and multiply it by that base, which is 2, and go up by that amount from the bottom floor. So this is telling me to go up 3, but then times 2, so up a total of 6. So 1, 2, 3, 4, 5, 6. So this point is currently 6 above the bottom floor. And if I want to get my next one, I'm going to move right 1 and multiply that distance by 2 as well. So 6, and then times 2 is now telling me to go up 12. So 6, 7, 8, 9, 10, 11, 12. And I went over too far. Let's go right there. And if I were to keep going, I would then go up 12 times 2, or 24 if I go right one more time. So whenever we go to the right, we're going to do exactly as the multiplier says, which in this case is to multiply our distance by 2. If we go left 1 from that initial point, we want to do the opposite of multiplying by 2, which in this case is to divide by 2. So if I am trying to go left 1, the distance of where I'm currently at is 3, and I need to do the opposite of multiply it by 2 and divide it by 2, or cut the distance in half, right? That's the same thing as dividing by 2. So if I'm up 3, half of that is 1.5. So I'm going to go up 1.5. If I go left one more time, I'm now having to take that 1.5 distance and go, or cut that in half, which is 0.75 from that bottom floor. And we can continue that pattern as far as we need to. But really just 1 or 2 points on either side of that initial point is going to be plenty. And we can see that we're starting to get really close to this horizontal asymptote. And so we can go ahead and connect all these. Now, maybe you just watched that and you go, what the heck did he just say? There's no way I'm going to be able to remember to do that on my own. Well, like we said right here, we can always tee it up. So what I could come down here and do is say, I don't remember my rules. We need to at least kind of remember where that horizontal asymptote is, but even if not, I can say, let's make a table. What's X? And then what are those corresponding Y values? And when I'm thinking about what X values I'm wanting to use, it really doesn't matter, but the best ones are going to be getting a couple points to the left and to the right of our initial point, which in this case is right on the Y-axis. And so all my points here span from -2 and -1, 0, 1, and 2. And so I could grab my calculator and I can check some of these. So why don't we do one real quick? And I'm going to see if I plug in -2 this equation, do I get the same Y value as to what I had right here, which to me, it looks like it's -6.25, I think is what I should get, or something close to that. So I'm going to go 3 and then 2, and then your exponent button is this caret button. Almost all calculators have that, including the phone calculator, which isn't effective. Don't be using that, please, unless that's the only thing you have. And then -7, and look at that, spot on of -6.25. And so I could come up with all the rest of the Y values and plot them and not even have to worry about these rules. So we want you to be able to do both. If I don't need to plug in values and I can use these rules, it goes much quicker. All right, so what happens as we start to change the graph now that we have a horizontal shift? Well, there's not much difference between how we want to graph this equation that has the x plus 3 compared to how I did the one that just had the exponent of x. What I'm going to do, though, is I'm going to recreate my new x and y axis. So this horizontal asymptote is kind of serving as our new x-axis, right? It's been our vertical shift. So we've taken that original x-axis and we've shifted it down 7, just like I did over here in number 5. This x plus 3, we first need to remember with any horizontal shift, we have to change the sign. So if it's x plus 3, that's really telling me to go left 3. And so I'm going to draw in a vertical line at -3. And this is representing my new y-axis. So all I'm going to do is recreate these same points, but instead of it being on the original y-axis, I'm going to put them on my new y-axis. So the first point, if we look back over here, was up 1, 2, 3 above that horizontal asymptote. So I'm going to go up 1, 2, and 3. My next point was 6 above that horizontal asymptote. So I need to go right 1 and up 1, 2, 3, 4, 5, 6. And the next one was up 12 from that bottom floor, or excuse me, yep, from the horizontal asymptote. So up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And I can get the same points to the left. So that would be negative, or right in between here, so halfway. So wanting to go down 1.5 and down 0.75, and then that should be plenty. So really the exact same graph, just all the points have been shifted left 3. And we do want to actually work on recognizing those horizontal and vertical shifts. It's going to be really helpful for when we start graphing the inverse of exponentials, which are those logs. You've just heard me talk about it. We haven't introduced them yet. So thinking about those shifts can be really helpful. Now, again, maybe you watched this and you said, I have no idea how the heck he came up with that. Let's make a table. So here's how the table would be different. We want our x values that we're choosing to be right along our new y-axis. So it's kind of based on that horizontal shift. And I want a couple points to the left and also to the right of that new y-axis. So if I were to plug in points, I'd actually want to start with -5 and then -4, and then -3 is essentially my new 0, right? So whatever I get for the y value here, I should get for the same y value at -3. And then a couple points to the right of my new y-axis would be at -2 and at -1. And once again, you can plug those into the calculator and figure out what y values you should get. Okay, let's go through one more example, one with the decreasing function, and then that'll wrap up the video for today. And once again, I'm going to actually use the rules and then just talk about the x values that you could plug in to come up with this equation. And maybe I'll show you how we plug in one of them now that our base is a fraction. So when I'm looking at this, again, I always start by recognizing where are my asymptotes, and looking at the horizontal asymptote, that usually shows up or always shows up after the exponential term. There's nothing there, which means my horizontal asymptote is the original x-axis, which is at y equals 0. My new y-axis, I see x minus 5, is shifted right 5. We got to think about that sign change. So this is right 1, 2, 3. Well, I already went right 5, so I don't know why I'm counting. And now we need to create our points. So once again, the a value is 4, telling me my first point is on this new y-axis, and it's 4 above our horizontal asymptote. So I'm going to go up 1, 2, 3, and 4. Now, if we follow the same rules for what I described before, if I go right 1, I need to do exactly as the multiplier says. This multiplier is 1/3. So I already know this is going to be decreasing. So my points as I move to the right should be getting closer to my horizontal asymptote. So 1/3, or multiplying by 1/3, is the same thing as dividing by 3. So essentially, if I move right 1, I'm wanting to take this distance of 1, 2, 3, 4, and I want to divide that distance by 3, which is about 1.33. So that's telling me I need to go down, or excuse me, up 1.33 from that bottom floor. So up 1 and then about 1/3 gets me right in that area. And again, it's just an estimate, right? I don't know exactly where 1.33 above that bottom floor truly is. And if I went one more time, I'd take that 1.33, divide that by 3, telling me it's 0.44, so almost halfway up from the x-axis to 1. And now I've got a few points to the right. Now that's not really helpful. We want to see kind of those points that have the whole number increments. And we're going to get those this time as we move to the left. So the opposite of us multiplying by 1/3 or dividing by 3 is to multiply by 3. So if I'm 4 above this bottom floor, if I go left 1 now, I'm having to go up 4 times the opposite of dividing by 3. So 4 times 3 tell me to go up 12. That takes me slightly off the graph. That's okay. I'm going to put it up here. This would be at 10, 11, and 12. And now when we connect our points, we see that exponential decay graph, and it decays pretty quickly. All right, so again, if I want to create a table, because I look at that and I'm like, I don't know how I came up with those points, then I'm going to tee it up, make a table of x and y. I want to think about what points I have to the left and to the right of that initial point, so kind of based on the horizontal shift. So I want that to kind of be in the middle. So the horizontal shift was 5, and it was right 5. I want 2 points to the left of that. So that'd be at 3 and then 4, and then 5, 6, and 7. So what I can do is I can literally come to my calculator and just plug x values in to the equation. I don't need to change anything. So 4, one thing I talked about in one of the videos was anytime you're dealing with fractions on a calculator, putting them in parentheses, and it's really just a division problem. So that's 4 times 1 divided by 3, and then to the power of x minus 5. If you're using an older calculator or an older Texas Instrument, it doesn't allow you to stay in the exponent like what I did here. So what you might need to do is after you, or before, oops, cleared everything. Let's get that back one more time, 1 divided by 3. After you hit your exponent button, you might need to put it in parentheses. So the calculator knows you want that x value, which is 3 in this case, minus 5 to stick together. The other thing that'd probably be even easier is do 3 minus 5 in your head, which is -2, and then you don't have to worry about that. So that'd be at 36, which we didn't graph. That's way above. So that one wasn't even on our graph. So let's get one that we actually did see. Let's make sure that we do that one correctly. Let's do 6. I want to see if 6 actually comes out to be about 1.33. So 4 and then 1 divided by 3. And this time it's to the power of 6 minus 5. I'm just going to type in 1. I'm not going to do the 6 minus 5 in my calculator. And sure enough, I get that 1.33, just like what I got when I use all my exponential rules. Okay, last one, and then we can sign off here, and you can complete your video checking. So now, again, we're going to create the same graph, just we have a different transformation. So this is telling me to go down 9 with my horizontal asymptote. This is my new x-axis. The new y-axis is once again at 5, so that has not changed. And so the big difference here is all my points are being shifted down 9. They're going to be the exact same otherwise. So my first point is 9 further down than the initial one, so that should be at -5. I'm going to see if that's the case if I use the rule still, which is telling me to go up 4 from the horizontal asymptote on our new y-axis. So if I go up 1, 2, 3, 4, I get to -5 just like what I expected by taking 9 away from that first point over there. And then again, we can just recreate our other points. So go up 1 1/3 or 1.33 from that bottom floor, and then up, what did we say that amount was? 0.44. And if I go left 1, I'm having to go up 12. This time, I can actually plot that. So 4, 5, 6, 7, 8, 9, 10, 11, 12. But I won't be able to go up 36. That's going to be too far. So this gives us all our points. If I were to make a table, because our horizontal shift has not changed, I would actually just use the same x values and plug in 3, 4, 5, 6, and 7. And that would give you plenty of points. All right, that is it for this video. Go ahead and complete your video check-in and have a great rest of your day.